All right, this. I don't know. We'll see how this talk goes here. Just as a disclaimer, this is probably some. This is like, I don't know. It's a work in progress. So it's kind of nebulous. I'm sort of thinking about how this relates to a PyCon talk in a month or so. So, how many people have messed around with PyPy? Just curious, couple people. Okay, so I've been kind of looking at it lately. I have not. I'll sort of admit that I've not done a lot with PyPy in the past. I've run it a few times, kind of tried it out. I'm sort of aware of it through the kind of the conference scene and blogs and stuff like that. Sort of recently been trying to wrap my head around what's going on inside of PyPy, and that's what this talk is about. So some things that you probably know about PyPy, unless you've been living under a rock or something. It's basically Python implemented in Python. Okay, so it's like a complete implementation of the Python interpreter in Python. It's apparently quite fast at a lot of stuff. If you run it, it can actually be significantly faster than CPython. I mean, I've done a little bit of experimentation with that. I've sort of found that for certain things, it might be 30 to 40 times faster than CPython. Other things, maybe it's like 10 times faster, but it is fast. A lot of smart people working on it, like Alex over here. But if you ask people how it actually works, from my point of view, it's total magic. I mean, it's like, I don't know whether there's like magic, whether there's like crushed up grad student souls in there or something like that. I don't know what makes it work. So, and just to be a little bit honest, it kind of scares me just a little bit. Not the concept of Python and Python, but just the implementation of it seems a little bit forbidding. I don't know, those of you who have looked at it, have you kind of looked at this code for it or anything, or did you just kind of download it? It's a pretty hairy thing, and I have this question. Is like, can I actually even understand what's going on in there as sort of a an outsider, because I've not contributed anything to PyPy. Can sort of normal programmers understand it? Like somebody who has like a solid background in programming understand it? Can you debug it? Can you modify it? I don't know. And one of the things I find really intimidating is the process of building PyPy from source. You're probably not going to be able to see this very well, but those of you who have tried PyPy, have you ever built it from source code? It's this really crazy thing. Actually, I could probably do it in the terminal here, just to let me find it here. So if you go into like the PyPy source code, the way that you build the thing is you have to go into sort of this deep down into the hierarchy, and then what you do is you run this like translation script. So you can say, okay, we're going to translate. We're just going to run translate, and then you can give it some options, like I want the JIT or something. And this thing will go off, and it will just, God only knows what it's doing. It starts running the C compiler, doing a bunch of. Do you know what's going on with this part of the platform check stuff? I'm going to ask Alex as the go-to expert on PyPy here.
Yeah, basically invokes your C compiler. It's sort of the same way a configure script would. You
Okay.
Size and stuff.
So it's just trying like different configure options and so forth. So it kind of cranks away and does some C compiler stuff for a while, and then I don't know, I'll give it a minute here, and then it will basically proceed to crank away on stuff for well over an hour on this machine. This is a quad-core modern MacBook with 8 gig of RAM. It'll take about an hour or 20 minutes or something like that to sort of run through it. I actually made a little movie of it. See this here. This is a movie of building it from source that I'm going to start here. And you're going to look at that and you're going to say, I have the fastest computer in the world if you've ever done PyPy. This is what it prints up when it builds. It makes like Mandelbrot sets. Goes up. That's actually running at 64 speed, 64 times faster than normal. So this is going to compile PyPy in about a minute as opposed to like 75 minutes on my machine. But the question that comes up with that is that, first of all, you need quite a bit of memory to do this. I have like an 8 gigs of RAM. I've done this on machines with less, and it took like 14 hours to build on my.
Finished?
It did finish, like on my laptop. I have like a regular MacBook. Took like 14 hours to build. Takes a lot of memory. What in the hell it's doing over here? I have no idea. I mean, with like all this Mandelbrot set stuff and C compiler and warning, and it's just like blasting away for like a long time. No, it's just one core because of the GIL. bring the GIL. You got to bring the GIL into everything. That's here. Okay, so now it's writing out C code. You can see the memory on the machine is like way up there. Actually, I missed that. But okay, so 4,500 seconds later, you now have like a PyPy interpreter. That's what it looks like to build from source. I mean, it's like this very intimidating thing. I look at that and it like scares the hell out of me a little bit. You know, it's like, what happens if it breaks? I mean, it's like, do I have any hope of fixing it? So, there is that, and then there's just this other thing that I think about, and this is just my own opinion, but I think like a big part of Python's success is actually the fact that people can tinker with it. Like if you go to CPython, a lot of people can mess around with that. I mean, it's like written in ANSI C. People know C. It uses make files, and it's documented. It's something that's accessible to a lot of programmers. Like you can mess around with it, do stuff. And as you know, I mean, there's a lot of documentation on CPython, you know, the high-level stuff. But you can also go pretty low-level too, like looking at what the C interface is and so forth. If you jump into PyPy, or before we jump into PyPy, I actually think this stuff matters in the big picture. Like the PyPy guys, you know, they want people to use PyPy. They want people to use, you know, adopt it, do things with it. I think that stuff kind of matters because as a user community, you want people to submit bug reports. You want people to make extensions and to port it and to play with it. And like all the stuff that comes into Python, I think a lot has come about because people have been tinkering with it. And so part of my motivation on this talk is actually just to kind of see whether you can tinker with PyPy, kind of what the status of that is, whether that's something worth looking at. And if you go into PyPy, you will find that it's quite a different flavor to it. You know, my own impression of it, I mean, it is sort of an advanced research project. A lot of the documentation on it is couched in sort of academic papers, conference papers, journal papers. A lot of presentations, like you go to PyCon, you see these presentations where it's like, oh, PyPy is really fast, and they show lots of benchmarks, but they don't really take you that much behind the scenes as far as like an implementation side of it. So fair amount of documentation, but it's not really very low level. Some of the high level documentation is stuff like this. They'll show you these like flow graphs of like, oh, it takes source code and it does this to it, and oh, it just annotates it and does that. There's a whole lot of detail missing from that, you know, like what it's actually doing. You can go to the tech reports, which is a really, if you can't read that from the back, you won't read it any better from the front. So, but there's this is like from one of their from one of the EU like progress reports on PyPy, and you know, I'm looking at that, it's just like, okay. In their defense, they have to write it like that. I mean, PyPy is basically like a funded research project in programming languages. And if they don't write it like that, they're not going to get funding. I mean, so. I mean, I can cut them a little bit of slack on. Actually, things like the academic programming language community makes Hacker News look like amateur hour when it comes to like flaming people. So it's there's that. The other thing you could do is just look at the source code. I don't know. That's its own adventure as well. So it is a little bit difficult to get into. And so what I'm hoping to do here is actually just kind of take you into a tiny bit of how PyPy works, and mainly just talk about the implementation language. There's this implementation language called RPython, and I've kind of been tinkering around with it. And really the whole motivation is just to look at it because I'm curious. I haven't done anything with Python, with PyPy. I'm not attached to that project. I haven't used it for any real project. I know of it just from the Python community. Like I know there's a lot of buzz around it. I know there's like some amazing things that people have done with it. So that's kind of my motivation here. Actually, the only thing that I've done for PyPy is I submitted a bug report about the GIL because it's my duty to break GILs everywhere. So that was my one submission there. So just as a little bit of overview, if you have not done anything with PyPy or you haven't seen much about it, it's basically an implementation of the Python interpreter in Python. Just to kind of give you an analogy of it, the Python that you're used to, like CPython, you have Python programs, like Fibonacci numbers or something, and it runs on top of a Python interpreter, which is written in C. You can download the C code from Python. It runs the interpreter. PyPy is basically that same idea, except that instead of having the interpreter in C, it's written in Python. Okay, so you have like Python running an interpreter for itself, essentially. And one of the things about PyPy is that you can actually run it as a normal script if you're so inclined. I mean, it's Python code. So if you want to, you can actually just run the PyPy interpreter as a Python program. It sucks. I mean, if you do that, I mean, it has horrible performance. It's like I haven't measured it. Do you have any idea, Alex? Like,
it's like on the order of 2,000 times slower.
Oh, 2,000 times slow. Well, you'll notice here that it took like 35 seconds just to start up at the interactive shell. Okay, so what?
The PyPy interpreter as a program in CPython interpreter, so you actually use script.
Yeah, you just run it in the Python interpreter. So like, yeah, it's just a script. So let me get out of here. So I think it's in like the bin directory of the distribution. So there's a script py.py. I haven't really looked at that in great detail, but okay, main entry point to the PyPy interpreter. You can just run it. So like if I type Python, it's Python 2.7. That's CPython, and you just type Python py.py. Now again, it runs the C compiler. I don't know what it's trying to figure out with that. So it does a whole bunch of little setup here, and then it kind of sits there for like half a minute or so, and like.
Why does it need the C compiler at all?
Don't ask me. I think there's some configuration stuff.
Yeah, basically
like,
all that configure stuff that is at compile time when you compile it, it's really just like a bunch of global declarations, so it gets invoked when you run it as a script as well.
I thought the whole point was not to have to. I thought the whole point was to do it in Python, not in C.
Yeah, it's still all Python code, but like we interface with C libraries, like for the select module, interfaces with a bunch of C libraries.
Why do you need to compile?
Basically to verify like the sizes of structs and other things like that. Because when we interface with a C library, we have. Are you familiar with the C types library?
Yeah, okay, so I understood that part about getting sizes.
Yeah.
Like the ink could be a different size or something.
Mm-hmm.
Yeah, stuff like that.
Yeah. Well, I mean, I think also running PyPy like this is not really the intended usage of it. Like you would never who would want to run Python running on top of Python that's like 1,000 times slower than Python. I mean, that doesn't make any sense. So, but I think the main point is that PyPy though is implemented in Python. So I mean, it's a Python program. If you run it on the Python interpreter, it will run. Now you might not get some of its features, like probably I don't think the JIT runs in this mode or anything like that, but it does run. You can probably mess around with it. But that's not really what people do with it. So what actually is going on underneath the covers is that PyPy is implemented in this thing called RPython. Okay, quote RPython. One thing about this RPython that, I mean, unless you've looked at Python, that's kind of confusing, is that RPython is not Python in any traditional sense that you might think of. In fact, it's not an interpreter, for instance. Like there's no you don't run some program called RPython. It's not an executable, it's not an interpreter, it's not anything like that. Essentially what it is it's just a subset of the Python language. So you take all of what you know about Python and then carve out this tiny limited subset of it. That's what RPython is, and I'm going to talk about what it is, what you can do with it in a second. But it's essentially valid Python code, but restricted in what it's allowed to do. And that's actually about the only similarity. Essentially, what this RPython is it's, for lack of a better analogy, it's like C++ in Python. It's essentially Python syntax, but you actually have to compile it like C, C++, or Java, and it does static typing like C, C++, and Java. It's all done through type inference instead of type declarations, but it's essentially a statically typed language. If you love a lot of the dynamic features of Python, like being able to put anything you want in a list or anything you want in a dictionary, you will hate RPython. Okay, I mean it's like it is not dynamic at all. We'll get to that. Yeah. C. Yeah. Unless I've missed something somewhere along the way.
In theory, you can also compile it to like JVM bytecode, .NET bytecode.
Yeah, let's not go there though.
No one uses it.
Probably the closest thing that I've used to RPython is ML, and it's been quite a while since I've used ML. I mean, has anybody used ML in like? Yeah, I mean, I used it in school. I mean, it was. Yeah, my impression of ML was like this really cool language, but you could never get anything to work for like hours and hours. Like what you would do is you would just code for hours and hours and hours, and you'd like it's like code type error, code type error, code type error, type error. You'd have like 5 hours of type errors, and then like magically all the type errors would go away, and your program would run, but you don't know why. Like you get the right answer, but you didn't know why. Is that kind of like your experience with ML? Was the
So going from Python to ML is quite a leap. Is it really like ML in the sense it's like functional? It's not Python at all.
It's not. Well, I wouldn't go that far, but the feel of it felt very ML-ish in the sense that if you had any mistake in the type system, the whole thing would just go belly up. Complain. So what I wanted to do is actually show you just like an example of how you write RPython code. There's actually just a little bit of stuff you need to do it. So I'm just going to do like a hello world program in RPython. Okay, so we're going to just do hello world. What I've got here is this is almost exactly like a main function from C. Like if you write C code, you have to have a main. Main has to take in an argument list, and it has to return an int. It's maybe bringing back horror memories or something like that. But the signature of main in C is int, and then you have like the arguments there. So I have like this hello world program there. To use RPython with PyPy, you only have to write this one function called target. And all it has to do is return the function that is the entry point to your program. What this is doing is it's just telling RPython what the starting function is. None, I think, is some options, I think. I haven't really looked into that. But
I want to say it's like an optional like compilation policy, which is deeper magic than anyone ever needs.
Yeah, just the none is deep magic. Don't go there. So that's basically an RPython program. Print hello world, return that. Now the question is, how in the world do you run that? So if you're normal Python, you would do something like this. This is like Python 2.7 kind of stuff. Okay, so this is like C Python. So if you wanted to run this in C Python, you might just put like a little main program on it, and then what you would do is just type Python hello.py, assuming that I saved it in the right directory here. Let me move it down one directory. Okay, there's hello. You can run that. Print out hello world. To do this with RPython, it has to be compiled. Okay, so RPython is not an interpreter in the normal sense. What you have to do is basically compile it, and the way that you compile it is you run it through this translate script that comes with PyPy. So this is part of the PyPy distribution. There's sort of this translation tool, and what you do is you say, okay, translate hello.py, and then you sit back and you watch. Okay, so it's not going to take an hour, but it does take a little bit of time. Okay, so
that's truly fantastic. It really is fantastic.
Really fantastic.
It's fantastic.
Yeah.
I can't believe that just happened.
Yeah. Okay. So 17 seconds. What it created is basically a program hello.c in your directory.
Just the fastest hello.
Yeah, the hello C is a 190K file, hello.c. It's probably, I don't know. Do you know what's in there? I don't know.
It's got the entire garbage collected.
Yeah, it's got the garbage. It's garbage collected. Come on, work with me. Okay, so, and then you run it. You get hello world. That's basically RPython in a kind of a nutshell. Yeah. So what, you like all the output from that?
Well, it boggles the mind a bit to wonder what it's doing there. But
well, that's what I
please,
thought. That's what this. Yeah.
Do the Python people or do the C Python people define the RPython subset?
No, I think the PyPy people are defining that. And it actually doesn't seem to be all that formally defined. I mean it's a little crazy there, but that's kind of an example of it. And then you run the translator, and it does a whole bunch of output. There'll be a quiz later on that. If you wanted to do a more complicated example, I mean, you could run like the Fibonacci numbers or something. I mean, that's kind of see what we're doing on time here. So this is just partly because the Fibonacci numbers are so critically important to everything here. Yeah, Node.js, since the well, if I were doing Node.js, I'd probably have to do this as like an async callback of some kind. Well, let's not go there. Okay, so here's sort of another example. It's just a program that's going to compute like some Fibonacci number, doing a really horrible algorithm on it. So we can try this one. Let's translate that. Just so you can watch the process again, it's very cool here. So
it's like downloading a whole GitHub.
Yeah,
repo there.
like a whole Git thing. Yeah, it really is impressive with the amount of output and the intimidation factor.
Like if one step was omitted there, that wouldn't have worked. Every step there is probably critical.
Yeah, probably critical to the whole. Yeah, so you do that. And we can try this out. Let's try I'm going to just do a timing test of timing. This is just going to be the normal Python version of this. So let's compute the 38th Fibonacci number and to see how long that takes. I don't think it takes more than an hour or so. There'll be a quiz on the compilation process later. Okay, so that took about 20 seconds to do that. Let's run the RPython one that we made with that. Well, you already got a sense that it's a lot faster. Okay, 0.49 seconds there. So you're looking at basically like a factor 40. I don't know because I don't know how to look at it, to be honest. I haven't gotten that far in my. Do you know how to? You probably know how to look at it. But.
I don't know wherever temp directory. It'll say somewhere now in all that output actually
where it goes, but I think it probably deletes it afterwards.
No.
Or it doesn't.
The last, I think 5 by default are saved.
Yeah. Okay.
C code's ugly though.
I'll bet. Yeah. Anyway, if you do this, it is pretty fast. I actually did a timing of this RPython code against ANSI C. It was not that far off, like 2.1 seconds versus 2.6 seconds. It's moving right along because it is compiling C code. Now, what's going on underneath the covers of this is going to kind of take us into behind the scenes a little bit. One of the reasons why this runs so fast is that RPython is basically statically typed Python. It's like C code, where you pin ints and floats and things. And the way that works is that it's doing some type inference on your code. Just to kind of give you an idea of that, if you have this Fibonacci code, it looks at it and it will say, you know what, you're calling Fibonacci with an int. I can just look at it right there, main. You're calling Fibonacci with an int. What's going to happen is that int is going to propagate through the code. So it will know, okay, the argument to fib must be an int. And then it's going to look at the source, look at the body of Fibonacci, and it's going to say, well, that's an int. It returns an int. So the return type of Fibonacci is an int. And essentially what's going to happen is the whole code gets annotated with types. And the whole thing is ends up being statically typed through this kind of type inference technique. And so that's why it's fast. But one consequence of that is that you actually lose almost all of the dynamic typing features of Python. By doing this. And I'm actually going to show you some examples of this. So one thing that you can try, let's just go back to the hello program here.
You had called that Fibonacci function twice with once with an int, once with a float. Is it like templates in C++? Would it generate two different versions of it?
I think, floats are a little, it might die, but we have to try that. What we can do though is it's kind of, let's say you had an add function, like that, and you said print add 2, 3, and then you said print add hello world, like that. That actually is perfectly fine in Python, right? Because that's dynamically typed, doesn't care about it. That will blow up in RPython. So if I try to translate that, it will sort of work on it for a little while, and then it will just blow up with a huge error message.
It drops you into PDB. No.
It drops you into PDB, actually, yeah, a version of PDB. And you kind of have to read through the error, but it's basically getting tripped up because you're calling function with two different signatures. So like that first function call is essentially the signature. Like, so you called it with ints, that's what it is. So you don't get any dynamic typing on function calls. So
I think it would split it into two methods.
That's what I would.
not that I'm aware of. Do you know if it?
No, if you want something like a C++ complex behavior or a Java's generics, there's like a decorator that lets you say, I want to use this way, but by default, it assumes that you have a single set of types for each method.
Yeah, it's very much statically tied. Some other restrictions of it: all the container types can only have like a single type in there. So like if you had like a list of numbers, that's okay. But if you had like a list that had a number, a string, and a float in it, forget about it. You'll get an error generating that. Same thing for like dictionaries. Like if you have dictionaries where it's all the same kind of data, like string keys, string values, that's fine. If you had values where one of them was a string, one of them was an int, it'll blow up. And really kind of the right mental model of it is to think of C code. It's like, with C, you have to have the types. Like in C, you can't make arrays really of like mixed types. You have to declare like a type, and that's what this is doing. Same thing for like classes. If you had like a class pair, for instance, self X, self Y, the types of those attributes would actually get fixed by the first use of it. So if you say pair 2, 3, it's going to go in and say, oh, those are ints. And if you try to assign it to strings, it'll blow up. So it's really kind of a weird programming environment in the sense that you don't have the dynamic features of Python. I mean, yes, it's Python syntax, but it is not at all like Python as far as like the semantic.
And what else?
You get
So
tuples.
As opposed to using C directly, this gives you sort of primitive data, high-level data structures, and that's probably.
You get high-level data structures, and probably one big thing you get is garbage collection. So like, not implementing like if you had to implement in C, then you have to write your own garbage collection. It's like a big mess, but it's essentially you get like a core set of data types. I think you get tuples, lists, and dictionaries. I don't think there's sets.
There are not sets.
Okay, there's not sets. There's actually a whole bunch of missing stuff as well. Like you can't use generators. A lot of the special methods. Yeah, some of the special methods don't work.
The only special methods that work are under, init, and under, del.
Okay, all the other ones are.
Calling out to external systems, you probably get into this.
Nah, probably not. But,
no. Okay. So, so then calling out, say, to Python libraries or C libraries. Is there any sort of candy for that, or is it just not possible?
Yeah, RPython has its own foreign function interface for calling out to like C or Fortran or whatever.
Yeah.
Yeah.
How does it infer its return type?
I think by what you just passed to the return statement.
Right, but if you have multiple return statements, you're returning types.
Well, my guess is that it would find the first one during like some kind of annotation pass, and then it would raise an error if you had mixed, like if you had two returns that had different types. Though I mean, it would eventually just go belly up, saying, "Hey, I don't know what you're doing." So one thing that gets a little bit wild with RPython, I don't know how much I want to go into this, but if you want to create data structures that have mixed data types, like let's say you actually wanted to have a dict that had like a string and an int in it. The only way that I could see to do that, and Alex can correct me, is to basically do boxing of values. And kind of the idea on that is you basically make like a base class that just says, okay, this is some value, and then you specialize it with like an int version of it and a string version of it. So you say, here's an int value, okay, some class. Here's a string value, some class. Essentially what will happen is you make your data structures hold instances of those types, and they will unify under the base class. So RPython will say, oh, this is a dictionary mapping keys to some value objects. Problem with that is that you have to essentially go through method calls to get into the internals. Like if you want to pull the value out, you have to call a method to do it. Similarly, if you want to store something, you have to wrap this class around it. So that's something that you have to do. Now, just as a few notes on this, if you read a little bit through the PyPy docs, the developers of PyPy seem to be somewhat adamant that users, especially like just casual end users, should probably not mess around with RPython. And I would, having looked at it, would tend to agree. I mean, it's not anything like the Python that you know about, other than like the syntax is the same. Semantics are quite different. There's a number of like really annoying things that it doesn't let you do. You know, it's great for maybe implementing PyPy, but it's kind of its own thing. So that's one thing to keep in mind. One thing I worry a little bit about is, you know, so I used to do a lot of work in like scientific computing, and I worry a little bit that scientists are going to look at RPython. They're going to say, "Ooh, it's almost as fast as C. I'm gonna go write like I'm gonna go write, you know, like molecular dynamics in RPython or something like that." I actually tried that, by the way, last week just to see what would happen, and it does run quite a bit faster than Python. I was getting like 40 times speed up doing that, but I was frankly quite annoyed at the code. Like I was actually cursing at it because of like things that were missing from RPython that I wanted to use, like you know, like the iteration protocol or something. You know, it's a lot of things that I wanted. So the final little thing I want to do here, let me see how I'm doing on time. I wanted to just say a little bit about what in the world is going on in that build process, like with the screens of the code. In hindsight, I'm not sure that I should have looked at this. I mean, I like last week I was like, well, I should go figure out what's going on with translation. Turns out that this is just diabolical, what's going on in there. I mean, essentially when RPython takes your Python code and turns it into C, it does it without doing anything normal like a compiler. At least that's my take on it. I mean, there's like no parsing. There's no like traditional operation of a compiler. Essentially what it's doing is it's operating entirely off of a sort of a live version of your code that has been imported. Like you take your Python code and you just import it into the interpreter. And this is like CPython, keep in mind. It's just like you type import, you bring all of your code in, and the entire translation to C is done by looking at the bytecode of your live program. Now, the way that just to kind of give you an idea on this, every bit of Python code that you write is compiled to bytecode by the interpreter. This is often not seen or by a lot of users of Python, but this is actually what happens under the covers. I mean, if you're in the
Is that the same bytecode for all the different backends? Java.
well, we're talking about CPython right now.
Okay. But,
We're just in, yeah.
but that's the whole point of PyPy, isn't it? That
This is a C Python
bytecode.
Yeah, this is just CPython right now. So, so one of the things that's bizarre about it is you basically start from like CPython, but you're going to hoist this thing up into RPython and then eventually into C. What happens is when you write Python, one of the things when you write Python functions, they actually do get compiled into low-level code. There is a library module called dis that will show you the disassembly of that. Okay, it's not very interesting for the add function, but it'll basically show you the sort of the low-level bytecode. It turns out that RPython is operating exclusively from that to build a C program. It basically takes your code it basically imports your code, brings the whole thing in, and generates C code straight from the bytecode.
So is it like doing a bunch of comparison on binaries? Like if some crazy binary then generate this C code? Like,
What do you mean like a crazy binary?
Well,
Like,
this is in Python, right?
it's in Python,
So
yeah.
then they're looking at bytecode. So you'd have to say, you have to be inferring some like abstract syntax to know this is, you know, how are they matching on that? They just, it must be an if statement.
They're just literally this. Okay, so yeah, I'll see if I can explain this. So they're going straight from the bytecode on functions. Those of you who don't know, the bytecode is available on a function if you go to the code attribute. And if you go CO code, it's literally a string of
they're dealing
bytecode.
with that, though.
That is what they're dealing
Yeah,
with.
that's what I'm
It's
asking.
that.
Yeah.
That. So
Like if /x02 then generate some other thing. Like that's what their code looks like.
that's what they're working from. Now they're not even trying to take it back into source code.
No,
Like,
the
but-
C.
Yeah, to go to
right?
C,
Yeah.
Yeah, they don't go directly to C, okay, but that's what they're working with. They're working with like the bytecode, and there is a lot of information underneath the covers, like the code attribute, the names of variables, and all sorts of other stuff. And RPython is basically working with this. It's not working with source code. It's working with that. Everybody still with me? The head explosion part. And so what happens here, and this is where my head starts to explode. It turns out that one of the pieces of PyPy is a bytecode interpreter in Python. Keep in mind that PyPy is Python implemented in Python. So as part of that implementation, there is a bytecode interpreter that runs bytecodes, okay? And it's written in Python because that's the whole point of the project, is to write everything in Python. So it turns out that there is this bytecode interpreter inside of PyPy, and the way that has been implemented is to be modular. It turns out that it's kind of this modular implementation where you can plug in objects into the bytecode interpreter. Okay, so what happens is this RPython thing takes Python code objects from CPython. Okay, so keep in mind we're in CPython here. And it actually interprets them using the PyPy bytecode interpreter in Python. Okay, so it's like, there's already like too many levels of Python going on. So, and so what it does is it actually interprets your code using the PyPy version of the bytecode interpreter. And then it actually records what it sees. So there's actually a recorder underneath this covers that is recording what's going on. And it uses that to build a representation of your program. I'm going to kind of take you through that. The font is small, and it's not going to diminish from what you're seeing in the back. So essentially what's going to happen is you have this stream of instructions. This thing gets executed in sort of what's known as like this abstract interpretation. It's going to run through the bytecode, and it's going to look at what it sees, and it's going to build this sort of graph of what's going on. The way that it's going to do that is it basically starts by creating like a block, saying, okay, here's a block of execution. There's a certain number of inputs to this function. Turns out that the inputs are just coming from the function here. There were 3 inputs to that. And what it will do is it will start basically executing instructions in the abstract, and it will monitor what happens to the stack frame that's associated with that. So it actually starts executing instructions, sort of manipulating the internal stack frame attached to that thing. Okay, so it's sort of it's kind of like an emulated execution. And then what happens is every single time it hits actually an operation of interest, like add something, like add 2 numbers, it actually makes a new block representing the execution of that one operation. And then it just sort of keeps going with execution. Okay, so what it's doing is it's sort of recording instructions in these blocks, and then it starts chaining blocks together. Okay, so it's like sort of recording what's going on, and so forth. And sort of every bytecode operation actually gets its own little dedicated block of execution there. I'm sure everybody's head is completely exploded by now. That's fine.
It's just deducing the block structure.
It's deducing the block structure, yeah. And then you get into some really weird stuff is when you start doing like Boolean jumps, like ifs, conditionals, and things like that. If you have these like jump operations, what ends up happening is the interpretation actually has to take both branches. This is really bizarre. Like in a normal Python program, you only take one branch. In this interpretation stage, it actually takes both branches at the same time, essentially, and follows them both. I'm not going to say how that works underneath the covers because it's utterly insane. But what ends up happening, though, is that the thing will basically follow the false branch for a little bit, do some instructions there, and then it will go up and work on the true branch for a little while, do some more instructions there. And then it literally will sort of follow both the true and false branches, kind of interleaved with each other until they join up at some point. So it sort of works through your code, building these like blocks, Eventually, after like massive head explosion, you will end up with sort of a graph, like a flow graph structure that looks something like this. So you're going to end up with all these little tiny blocks where every block is basically a single Python bytecode or a single operation, like add, subtract, multiply. From there, it does a little bit of simplification to not have so many blocks. Does that. And that's actually just the first step for the rest of the interpretation problem. So if you look at that, like those screens of code that are going by, that's basically what it's doing underneath the covers. It's literally working off of like the bytecodes and like doing sort of this interpretation of your code and building up like a big structure from that. Now, after it does that, okay, so that's just the starting point. It turns out that it starts to get even more insane from there. What actually happens is once it makes that flow graph, it actually tries to annotate it with types. So go in and say, oh, okay, I'm going to put types on this. And one of the things that happens is as it's scanning that, if it finds any new functions or any new features, it will recursively go do the same thing for those. So what it will do is start at the start of your program, make one of these graphs, and then it will sort of enter this discovery phase where it will just recursively explore all of the branches of your code and then build up a huge graph structure from that. Does that sound about accurate from?
Yeah.
Yeah, okay. So it will sort of do that. It will do that until it sort of decides that it can't do anymore. Okay, so it's actually this recursive algorithm. It just sort of does it over and over and over and over again until it reaches essentially what's known as a fixed point where like nothing changes, and then it's done with that. And so your head just completely explodes. Actually, I've been spending the last couple of days just trying to wrap my brain around like what in the hell is going on here, and it's like extremely non-trivial how they do this. So it turns out that that's about as far as I've gotten with it. At this point, I think I'm out of time anyway. But that's sort of a small taste of sort of what is going on with PyPy and like how it's built. I mean, essentially, you have this interpreter written in the subset of the Python language, and that interpreter is converted into C by directly analyzing its underlying bytecode structure. It's a little bit insane. It makes my head hurt. And so forth. One challenge in looking at this, if you're going to go exploring, is just figuring out what is going on. There's sort of PyPy interprets Python code. It's written in Python, but RPython is written in Python, and parts of RPython use PyPy. And like it's like at this, it's sort of like just the head just completely explodes on looking on the source, sort of figuring out what it is that you're actually looking at. So that's kind of the end of this talk. It's a little bit incomplete. It's kind of work in progress. I just thought I'd sort of throw it out there and just sort of see I'm seeing like lots of really scared looks.
Now we'll present Lisp, which is what this guy's going after.
So David, can you now submit a bug report attached to Python?
No. I'm not even sure, like, I don't even know how many people look at this one of the things that with this translation problem is just like, why does it take so long, and like how would you fix it if it broke? Like if it breaks, I'm not even sure what to look at.
So
and I'm just trying to
the devilish problem with interpreted imperative, bytecode VMs, where if you're going to infer the code structure from bytecode, you have this problem.
Yeah.
It's there. And these guys have actually tackled it, which is pretty fantastic.
It's pretty amazing what they're doing, actually. I mean, like, looking at it, it's insane. And like this whole bytecode interpretation thing that they're doing is just, I mean, it's quite crazy what they're doing there, because they're basically, I mean, I'll see if I can even explain. They're basically using the bytecode interpreter from PyPy, but they're doing all sorts of crazy workarounds to capture its state. Like what ends up happening is they like execute bytecodes, and then this capturing tool actually raises an exception to cause the whole thing to die. But then the exception gets caught, and then the piece of code that catches the exception goes in and grabs the state of the interpreter and like saves it, and then it will restart. Like it will basically
incrementally go down.
Yeah, it will like incrementally go through the codes, and it's like doing all this exception handling, and it's doing all this like bookkeeping of like states and frames and all this stuff, and it's just like.
So for things like scanning your code to detect errors, or it could be used for more than just generating code. It could be used to potentially document things and draw pictures on.
I don't know. The thing that I think is amazing about it is the fact that it works off of like a live image of your code. Like it's not even looking at the source code of your Python code. It's like it's entirely off of these like code objects. It's just I don't know. I find that amazing. So
are they like simulating the runs so they know which path to optimize? That's the path.
without knowing more, I would just say yes, probably. One thing I ran into, I wasn't able to reproduce it for this talk. Maybe I don't have a coffee or something like that. I actually ran into a problem with RPython where I had some program that I was going to do like a performance test, and I tried to translate it, and the translation was just sitting there for like a really, really, really long time, like 5 minutes or like just sitting there doing nothing. And then it produced this code, and I realized that it actually did the calculation in the compiler, and like it optimized it and just printed out the result. So I'm comparing this thing to Python. It's like, oh god, okay, the Python version of it takes like 2 minutes, and then the PyPy version takes like 0.01 seconds or something like that. And, sort of the fact that it got completely optimized out. It was like like a million iterations of some loop. I wasn't able to reproduce it for this talk, but it's,
So that would be faster than the C code.
yeah. I don't know. I probably just scared everybody off of PyPy. I am kind of interested though in just how this stuff works, though. I mean, I don't know, kind of a gearhead, just sort of.
How complete is it compared to CPython 2.7? Can you run any CPython program?
I think it's pretty. It's pretty. Yeah, I think it depends on how many extension modules and.
I think it's at the 2.7 level now, isn't it? As of the last
Yeah.
And does it now port to the JVM?
I don't know the status of that. Do you know about the JVM port? Is that?
So JVM and .NET, and I think those are the only ones. Backends exist for the RPython compiler, but the PyPy interpreter itself cannot be compiled with them because it uses features of the language that those backends don't support.
I don't know. Yeah, I think it just scared everybody off.
The PyPy itself is actually a little faster.
Yeah, or even a lot faster sometimes.
So I can write Python code and then compile it into JVM bytecode.
Not arbitrary Python code, RPython code.
Only
Mhm.
RPython.
Yeah, what's the option to do that? Do you know? Does it even?
Dash something equals JVM.
It isn't the.
Yeah, this isn't in production anywhere, is it?
Do you think it's like minus O JVM or something?
No. Try dash help. It's probably in there somewhere.
It has to run the C compiler for the help there. Minus.
It's above these. Somewhere
Oh
at the top.
man. Standard object space.
I feel like I'm looking at the output of the figure head.
Yeah, it's pretty.
Yeah, somewhere in there, I think.
Somewhere in here.
And I guess besides the
I don't know. I don't know. Yeah.
Just search for JVM in the output. Shove that into a file.
Start screen.
It's also supposed to make staffless Python, which is
I'm not gonna. I don't know. Yeah, except they don't show me the option above that, so just grepping for it there. So I don't know. I'm out of time anyway. So, but that's just a little taste of what's going on in there. If you're gonna go jump into the PyPy internals, I don't know. Would I encourage that or?
The rest of the internals are not nearly as scary as this. I swear. Mostly.
Mostly, yeah. Okay.
So does it do stackless Python with
I know there's a stackless option.
Yeah,
But
PyPy can be built with stackless enabled, and the next release that'll be the default. That doesn't mean there's no GIL though. That's totally independent of the GIL.
you're not getting that lucky with the GIL. All right, I'm done. So we'll have Alex come up here in a second. So.
All right, so here's what we're going to do. Stay seated. We're going to take a break in a second. But I also like the idea of introducing. We got a large group, not super large, but very manageable. And we're going to introduce, but we're going to do it in thirds.